In this video, we're going to work a few application problems using exponential equations. So, for this first problem, Delilah put $5,000 in an account that pays 1.7% interest compounded monthly. How much is in the account after 10, 20, and 30 years? So this is a compound interest problem. So we have 1.7% interest. Again, we need to take that into a decimal, so 1.7 divided by 100 would be 0.017. So that would be our interest, but we're compounded monthly, so that's going to be 12 times per year. So, using our growth by a percentage, we know that our ratio, what we're going to multiply each time by, is going to have to be 1. It's interest. We're growing, so it's plus. My interest rate is 0.17 divided by 12, because she's going to get 1/12 of the interest every month. And this is going to just give us 1 month. So when we write our equation, we're going to say the amount she has, she's going to start with $5,000. And we're going to go that 1 plus 0.17. Nope. Don't do that mistake. 0.017 divided by 12. And normally we'd say it to the x power, but this means x is in months. I'd rather have years. So I take care of that by making this 12x. So then x is going to give me, after 1 year, 12 times x is 12. I get 12 months for 1 year, 24 months for 2 years. So this is going to be my equation. To figure it out, to answer the question, after 10 years, we're going to take 5,000 times 1 plus 0.017 over 12 to the 12 times 10. And that's going to give us $5,925.81. After 20 years, we do 5,000 at 1 plus 0.017 over 12 to the 12 times 20. And that's going to be $7,023.05. After 30 years, stay put please, 30 years, we get 5,000 times 1 plus 0.017 over 12 to the 12 times 30, which will give me $8,323.45. In general, when we are doing money problems and dealing with compound interest, and we talked about this back in sequences, but stay put. Stay put, please. There we go. Compound interest. We're going to go n times a year. And your formula is you're going to take your principal, or your starting value, times 1 plus your interest, divided by the number of times you're compounding per year, and you're going to run that to the nx power. For our second problem, Darcy has $1,000 to put into an account, but she needs the money to double in 10 years, and we need what interest rate is she looking for. So we have $1,000. So y is going to equal 1,000 times some b to the x. Now we need it to double in 10 years. So when x equals 10, y needs to equal 2,000. So we can just plug that into here. 2,000 equals 1,000, b to the 10th power. And now we just solve this. We'll divide by 1,000. And we'll get 2 equals b to the 10th power. Now we need to undo a power, so we're going to undo it with the reciprocal power. 1/10. And b is going to equal 2 to the 1/10th power, which is 1.072 approximately. So I could plug that in here for my b. Y equals 1,000 times 1.072 to the x. But I don't care about the equation. She just needs to know what's the interest rate. So I come back to, this is growth. So your multiplier, your ratio, is going to be 1 plus your percent growth or your interest. So I know 1.072 is going to be 1 plus my percent. So my percent is going to equal 0.072, which gives us 7.2% interest. So Darcy's going to have to find 7.2% interest on her money, which is, she's probably out of luck, because right now interest rates on regular bank accounts are usually less than 1%. So good investment might give you a couple percent. We're going to have to look into more high-risk investments here. For our last problem, Daisy's up to bat, and she has done some experiment of her own, and she has collected the following data. We need to write an equation to model this data. So anytime you're going to need to do this, write an equation to model data, in order to choose what equation, what form you're going to need to use, you need to look at the scatter plot. So let's plug this table into the calculator and have it generate a graph for us. As we look at the scatter plot, we notice it looks like a nice exponential curve, which is what you would expect considering this is a problems about exponential functions, but we still got to take a look and check. And the important thing that we're going to notice on this one is that it doesn't level off at 0. It's going to level off here at 50. And remember, we're going to call that our asymptote. And this is at y equals 50, which means for our problem, we have a vertical shift of 50. As we look at writing these equations, we can deal with a normal exponential that decays down to 0 or starts at 0. If we have an asymptote anywhere except the x-axis, we need to consider this a shift. So I'm just going to shift all my data down 50, and I'm going to do that easily by making a new column, and I'm just going to take 50 away from all of the values and go from there. So I've shifted my data by subtracting 50 from each number on here. So now I'm going to write the equation for the blue numbers. So I'm going to take advantage of my point ratio form, which is y equals y1 times b to the x minus x1. So we can start at any point. And let's start with this point right there. So I'll plug this in for my x1, y1, and I will get y equals 79 times b to the x minus 6. Now to find my b, I need to select a second point. I'm going to pick one not too close to the first point. So I'm going to pick This one where x equals 24, plug that in for x and y. So I'll say 2.5 equals 79 times b to the 24 minus 6. And then I'm going to go ahead and solve that equation for b, because I know everything except b. 2.5 equals 79 times b to the 18th. I'll divide by 79. Since I know I'm going to have to plug this into my calculator eventually for my root, I'm not going to bother to do it every step along the way. So I'm going to leave this as a fraction for now. 2.5 divided by 79 equals b to the 18th. And again, to undo my power, I'm going to use the reciprocal power. So I take everything to the 1/18th power. And 2.5 divided by 79 to the 1/18th power is going to be about 8.825. So that's my value for b. So plugging this in for my b in my original equation, I'm going to get my equation for the blue data is y, draw, don't move, y equals 0. Where does that come from? 79 times 0.825 to the x minus 6. Now, all I have to do is shift this back to get my black data. So I'm going to take my 79 times 0.825 to the x minus 6 and shift it up 50 by adding 50 onto that. This is my final model. I'm going to check it to see how reasonable it is. So I'm going to just graph this on my original scatter plot, which you can easily do with your calculators. When I do that, I get this graph here. And you say, I'm not exactly on here, but if you look, that point looks good. That one doesn't. That's a little bit off. That one looks good. That one looks good. This looks like an awesome model for this data I have. Always when you're writing these models, take the time. Plot your scatter plot. Plot the equation. Plot the model. See that it makes sense.